So I will continue in my discussion towards approaching slow flow towards the standard model, the issue of symmetries, selection rules, and naturalness. So there are, as you well know, there are two classes of symmetry that are relevant in quantum field theory. The first class is gauge symmetries. So gauge symmetries are actually redundancies that are needed to write in a manifestly local and Lorentz invariant way the Lagrangian, the action, describing the dynamics of particles with spin higher than 1, higher or equal than 1. So in that sense, they are not real symmetries. And in the very same sense, there's no notion of explicitly broken gauge symmetry. A gauge symmetry, it's either manifest, okay, when you use the redundancy, or it's gauge fixed, okay? Those are the only two options. Okay. Also, when you add a mass to the photon, you can always undo the apparent breaking by adding the suitable Goldstone boson that nonlinearly realizes the symmetry and have a description which is manifestly gauge invariant. So in that sense, they're not real symmetries. And then there are global symmetries. And global symmetries may or may not be exact or fundamental. In fact, let me add a comment related to what we were saying in the two previous days. Global symmetries may well be, under all circumstances, emergent accidental symmetries, very much like parity is an emergent accidental symmetry of QED. It emerges simply for the fact that QED in the long distance limit, in the limit where you neglect all irrelevant operators, does not have sufficient wealth of fields to break parity. Okay, it cannot. Okay. On the other hand, whenever the wealth exists, and that's, for instance, in standard model, parity is broken, and so is CP. While CPT is not, because it cannot be broken by local Lorentz invariant quantum field theory. So it looks like nature, whenever it can break a symmetry, it does break it. Okay, but perhaps other symmetries may be exact. I don't know. My personal opinion is that, or impression is that, global symmetries are, under all circumstances, accidental approximate symmetries. And normally, okay, let's say normally, and this is from our understanding of particle physics, what we see and what we don't see all together. Accidental. So when you have, and even if they have this status, okay, of being accidental and approximate, they still play an important role, okay, in order to, when trying to understand the dynamics of a system, and the relevant word concerning the role of approximate global symmetries is selection rules. Okay, selection rules is the way the effects of breaking. Selection rule control the way the effects of breaking appear in observables. So the use of selection rules gives you a direct understanding on how a certain observable can depend on a parameter that transforms under symmetry and therefore breaks it. Okay, and the standard example of selection rules is from atomic physics, where you have either dynamical examples and photon transitions, okay, that are controlled by the would-be broken rotational invariance when you treat the external photon field as an external background. Okay, you have dipole, quadrupole transitions and all that. And similarly, more simply, as I will discuss in a second, in the static case, okay, just rather than studying emission of photons, you can consider an atom in an external constant electric field. Okay, under this circumstance, if the electric field is small, the rotational invariance of the atom is broken by small effect, a small effect associated with the directionality, the preferred directionality of the electric field. And the effects, physical effects of this external electric field are several physical effects of this external electric field can be quickly read out with the use of selection rules and symmetry. So an example of that is the mixing. Okay, when you turn on an electric field, put an atom in an electric field, you will have that only angular momentum in the direction of the electric field, let's say J dot E over E is conserved, okay, cylindrical symmetry, the other components are broken. So energy eigenstates will be characterized only by this quantum number and their energy, okay? And in particular, they will not have, in general, definite value of total angular momentum, J square. And so a given eigenstate will have mixing, okay, will contain components of different total angular momentum. So given an eigenstate, some state which has energy eigenstate lambda, so H and cylindrical angular momentum, I mean angular momentum in the direction of the electric field M. Okay, this is my okay. This eigenstate will involve will be a linear combination of states with the different definite total angular momentum, and you can measure this mixing in the following way. You can project the state lambda m. In fact, let me also say, let me keep alive that this is m, okay, angular momentum m, and let me also vary E, okay. So this is the family of eigenstates that satisfy this condition. The angular momentum in the direction of E is m. The energy is lambda, and I choose and I vary them, okay, varying E. So in general, if I have two E's, E and E prime, and E prime is some rotation of E, okay, with a given three-dimensional rotation. If I consider the rotational, the representation of this rotation on the Hilbert space, U of R, with U of R on lambda ME, I'll get up to a phase. I will get the same energy eigenstate in a situation where I have the rotated electric field. Okay, I find the eigenstate of another experimentalist who's using the electric field in a different direction up to a phase. Okay, some phase which I don't need to specify. Okay. Under this condition, I can so the mixing between different levels can be measured. Perhaps I'm making things more complicated than they are. It can be measured by considering the matrix element lambda m E with some state of definite J and J3. Okay, and the mixing between states different angular momentum, you can take them by taking the computing the amount, the product of the projection on this and on the other. So for instance, just to eliminate any phase ambiguity, let me take the star of the other one. So lambda ME, J prime, some other angular momentum, and J3 prime. Okay, so this is the quantity I can consider. It's considered as a measure of the mixing. Is the product of how much of one angular momentum and how much of the other is in the same state. Okay, that gives you the level of the mixing, the amount of mixing there is between these two states. So this quantity, I can call it like M, J. I don't know how to say it. J prime, J prime, J, E, M. Lambda E, okay, whatever, there is E. Let me drop M and the other, that's E, okay? And then there is J3 prime, J3, okay? And now it's interesting to see how this symmetry, this object transforms under rotations, okay? If I now apply a rotation here, okay? If I rotate the electric field, okay? Up to a phase that goes away, this is equivalent to putting the matrix here, the rotation U here, and U dagger there, okay? But now this, you can use just the action of this matrix on the states, okay? And this is going to be equal to the representation of type J prime. Am I using the right notation? I think I'm using the wrong notation. Sorry, guys. 1 second. Yeah, bars. Okay, let me use the bars here. J3 prime bar, R of J, J3 bar, of the quantity is just acting as so it's M of J3 bar prime, J3 bar of J prime E. Now, okay, so we have this equation, this relation J3 prime, J3 J prime J. There is more notation than is needed. Let me eliminate the J prime here. Let me just say this is E, and this is the rotated E. Okay, that's it. So what you have here, you have on the left-hand side a quantity that transforms like the tensor product of two J and J prime representation. These guys here are like R of J prime tensor product with R of J, and just by using the theorem and addition of angular momentum, this will decompose in irreducible representation with angular momentum J minus J prime, and so on and so forth, J minus J prime plus 1, J plus J prime, okay? And so the same transformation property should be matched on the right-hand side, and then, but on the right-hand side, the transformation is obtained by acting with the rotation matrix on the electric field, which is a representation of J equal 1, okay? Here, and when we expand, if the electric field can be treated as a small quantity, which is to say, the symmetry, the breaking of rotation is small, okay? So rotation is an approximate symmetry. So by definition, that amounts to our ability, to our possibility to expand this in a power series of E. Okay, so this is going to be a general polynomial in E, and at each power in E, we will have a certain direct sum of representations. Okay, if you take 1 power of E, you have J equal 1. If you take 2 power of E, you will have J equal 2, 0 and 1. Actually, 0 is not there because of anti-symmetry. So you will have up to, if you have n powers of E, you'll have up to J equal n, okay? And this transformation should match what you have here. And here, the smallest representation is J minus J prime. So that means that here the lowest power of E should be E to the j minus j prime. It is telling you that the mixing goes at least like j minus j prime powers of e. Okay, it tells you right away. Okay, symmetry tells you right away what should you expect for this mixing. Okay, then you can do the computations. You will do perturbation theory. It's going to be, and then you may find that it's smaller than this. So what do you think? You will find that it goes like there's not some additional power. What would you think? You think that probably you've missed some other symmetry, okay? Okay, perhaps parity or something else, okay? Or perhaps it's because you've chosen a very specific atom that by accident has a cancellation, okay? But of course, in order to have this cancellation, you need a very large multitude of atoms, you would expect, okay? It's very unlikely that the first atom you try has the cancellation for no particular reason, okay? But it could happen. These things happen. I mean, I had a flat tire in the middle of the Mont Blanc tunnel, okay? Right in the middle, okay? So things happen, okay? But generically, you expect this. This is what you're going to have, okay? And so that's our understanding of, so that's the natural expectation, okay? That's the natural expectation. Everything else, it's either you've missed some symmetry or you were lucky or unlucky, okay? There was something, okay? Depending how you look at it, okay? Now, in field theory, you have something similar, okay? Exactly the same logic is what underlies our understanding of typical, that is a natural situation, or a typical situation, a natural situation in quantum field theory, okay? Any questions? Okay, I'll go to quantum field theory. So in quantum field theory, so what you have couplings, okay? So let's say let's be definite. You have some fundamental theory, or you have a theory where the fundamental theory is very high scale, and you went to very, very, very low scales. And as it happens, as I was discussing in the first two lectures, a lot of structure decouples, okay? All irrelevant operators decouple. Decouple means their effect becomes smaller and smaller, and then you're left with a finite number of relevant or marginal couplings with which you do physics. That's what we normally do, for instance, in QED. Okay, when you do computation in QED, you just take alpha electromagnetic, and of course, if you're very, very precise, you can start considering also all the other effects. But and then you compute observables to sensible accuracy in terms of these parameters. Normally these parameters, I mean, it just takes your creativity. You can assign to these parameters. You can. So here we had a field, okay, the electric field. You can say it's a field, okay, it's not a parameter, but I mean, once it is there, it's constant. I mean, from the point of view of atomic physics, that's just a parameter, okay. In the case of quantum field theory, we have parameters. They're not fields. In fact, they may well be fields. They may be different in different points of the universe. They may vary very, very slowly. They may have been different at previous times. Of course, there are experimental constraints that I don't want to take this seriously. But you can think, you can extend, I mean, ideally, these parameters to fields just just technically, and assign to them transformation properties. Then at the end of the day, you just set them to constant, okay? When doing this promotion of parameters to fields, there's a whole set of symmetries that become visible, okay? And under these symmetries, the parameters transform, okay? And you can use, if the parameters are small, or small in the sense I was saying before, you can do perturbation theory in them. You can use these transformation properties of the parameters to very directly, okay, foresee how these parameters affect observables, okay? By the way, notice that the simplest example of use of selection rules, you learned it probably the Russians, they learned it in high school or elementary school. I learned it in at university, okay, the beginning, okay? It's just dimensional analysis, okay? Just dimensional analysis is just the application of selection rules associated with generalized dilatations. Now, in quantum field theory, the only dilatation we do, we dilute. We have only one dimension for quantity, energy, and we dilute that. But when you go to the domain of other physicists, you have a list like this of units, and you can change the units of all of them, and then you apply dimensional analysis. There's just a direct product of dilatation symmetries for all units. Okay, just change centimeters, liters, whatever, grams, Ørsted, whatever, all that you have, and you can do. And dimensional analysis is just a way to. So the quick check of the frequency of the pendulum using dimensional analysis is just an example of selection rules in classical physics. So you can do you can extend this game in quantum field theory by promoting couplings to quantity transform under symmetry. Okay, so given a set of couplings lambda I, you can assign to them transformation properties. Example: chiral symmetry, dimensionality, of course, some SU, some group, some compact group, some dimensionality. You can even extend them to fields, and then it will transform. You may even make them transform under Lorentz transformations. Okay. In supersymmetry, you can extend them to superfields, and a lot of interesting results in supersymmetry, all associated with the Seiberg duality, even a lot of the exact results that we obtain in supersymmetry simply follows from promoting couplings to superfields. Okay, so function not of space but of superspace. And in fact, you will see that the A theorem that I will discuss in the next future amounts to promoting formally the metric of Lorentz space to a dynamical metric. Of course, we know gravity exists, but that is done purely for a technical reason. Okay. Okay. So now, when you have, and you can assign symmetry transformation properties to this coupling. Now, under these situations, observables, okay, will be observable that transform in a given way under the symmetries that you defined. It's like the typical example of this that works very well in the standard model is decay amplitude, scattering amplitude, decay process in flavor physics, where you have the whole symmetry of flavor. Okay, you can assign in the standard model. Just think of it and explain it in this is like an exercise. Show that the standard model has an SU3 to the fifth. In fact, there's a U3 to the fifth symmetry associated with quarks and leptons, and assign transformation properties to Yukawas under the symmetry, and just try to see. And now this symmetry is a symmetry which allows you to control amplitude with different flavors. Okay, and when you do flavor physics, it can turn out to be useful. Okay, so that's an example. So when you have this situation, you can compute so observables. Okay, as it's often the case, in quantum field theory, observable will get all possible contributions that are allowed by symmetries. That's just the totalitarian principle first proposed by Gell-Mann. All that is possible in quantum field theory is compulsory, so because of quantum fluctuation. So here you will get all possible contributions, some observable. Let me just say it this way. Some observable is in general the sum of this is a different I, this is I, of different contribution to these observables, and each contribution, I'm giving some idea here. I don't want to be, I'm not making a big theory out of this. I'm just tell you what you get in practice, okay? So, and each of these observables will be, each of these contribution, there will be some numerical factor that may take hard time to compute precisely, but you can often guess, okay, if you have some practice, and you will have powers of, let me use the same notation. Yeah, you will have the first coupling to some power and one. Of course, this can be matrices, so you can have more complicated things. I'm making it simpler. Some n, n of n, okay, in such a way that this transforms in the way this observable transforms, and all these all these contributions transform in the same way. Okay, so we have various contributions. That is often what happens. For instance, I think again in flavor physics, you can have various contributions to the same amplitude going through the charm, going through the top. You can have various contributions, and I think also in neutrino physics you may have seen something like that, although I'm not sure. But certainly if there had been a lecture on flavor, you would have seen there are more contributions. Well, there's an example is epsilon k. Okay, contribution from the charm, from the top, and again now, and this thing is and this dependence is fixed by selection rules and dimensionalities. For instance, the dimension of this should be matching the dimension of these guys. Okay, this is just the simplest selection rule of all dimensional analysis. Okay, and the underlying symmetry that we use there is dilatations. Okay. Now, normally, therefore, so this is our estimate of the thing, and a typical situation is that while there may be a dominant contribution, there may be some smaller one, but this gives you a generic result. Now, the abnormal situation, the one that we consider abnormal, and therefore we could call them unnatural, meaning that there is something that we are not fully understanding, or just that there is a chance that we could not foresee simply based on symmetry, is when the experimental result, the experimental measurement of this quantity, okay, or the final result is much less than the maximum of this contribution. Let's say, so you have this theory of several parameters, okay, lambda I, and there are various contributions of these parameters to this observable, okay, and then when you vary these parameters, you can have you can explore the space of values of this observable, okay, and then you can measure this observable, and then what you find out is that some parameters are fixed, some other are not, and then you find that the only way to get the right value of this observable is if there is a cancellation between different contributions. In other words, you are in a situation where the value, experimental value, is less than the maximum of all these contributions. Okay, this can happen. Okay, this is a logical possibility, and when this happens, we say, okay, there's nothing wrong with this, but we just say that this situation is unnatural, okay? It's not typical. So unnaturalness is, if you want, a failure of selection rules, okay? Selection rules here fail to give you the offhand estimate of the result, because there's a detailed cancellation between two contributions which are in principle unrelated and transform in the same way, but they are depending on different coupling. Okay, so this would call an unnatural situation. On the other hand, what we would consider, so if a natural situation is one where the smallness, the observed experimental smallness of this quantity can be easily accounted by taking the coupling small, okay, and sufficiently small. And now, in this situation, however, when the coupling or the corresponding coupling becomes small, as I said, this coupling transforms under symmetries. In this situation, the symmetry becomes better and better, okay? Because in the limit where the coupling goes to 0, you gain a symmetry. These are coupling transforming under the symmetry, okay? So in the limit where there's 0, where the coupling vanish, there's nothing transforming under the symmetry in the parameters of the theory, so the theory is invariant, okay? The breaking of a symmetry is always measured by how do couplings transform under the symmetry. If the corresponding coupling are set to 0, then, and again, so this is okay, you can associate, according to this language, small quantities to approximate symmetries. Now, of course, this is a bit of a squishy concept, okay? Because again, you could go on forever, okay? You may even ask yourself, okay, you have these couplings in this theory, but how are they self-consistent? Can their because you can form combination of this coupling that transform in similar way, and that can be very, very different. Okay, the question is this a natural situation? Because in the end, these are observable coming from this coupling, but this coupling themselves could be coming from a more fundamental theory and be viewed as observable that you compute from the more fundamental theory. Very much like the coupling of the standard model can be treated, now that we have done all the measurements, as the observables, and the underlying theory is string theory or some other crap. Okay, and then the question is whether these couplings are these couplings are natural, and then you can go on forever. Okay, so that is why it's a bit of a sometimes confusing subject notion. So let me give you some example of naturalness and also some example of selection rules. Okay, so for instance, just this is a little exercise. This is on selection rules, not on naturalness. Okay, consider for instance a theory like this. Okay, d phi square plus lambda phi cube in 6 dimensions. Okay, 6 dimension simply because in 6 dimension lambda is dimensionless. Okay. And in this theory, you can do Feynman diagrams. You can easily see that the 2 to 2 amplitude goes like lambda square. The 2 to 3 goes like lambda cube, and so on. So the endpoint amplitude goes like lambda to the n minus 2. Okay? Try to derive this result using selection rules. Okay? That's an exercise. Okay? In the limit where lambda goes to 0, try to see how this can be explained by selection rule, just for fun. Now, instead, let me give you an example of natural parameters. Okay, and this is the well-known example of the pi plus pi zero mass difference. Okay, let me just erase here. So in QCD, take QCD. And consider the limit where the quark masses are 0. Okay, just for in fact, let's forget the strange. Let's just for simplicity focus on 2-flavor QCD. Okay, let's forget strange. Let's just up and down. Okay, in the limit, in this limit, check that in this limit there is an unbroken global symmetry, a global symmetry which is exact in the theory, but spontaneously broken by the QCD vacuum. Okay, and that the pi zero is the corresponding Goldstone boson. Okay, just think about this. I don't know whether this is too difficult. No, okay, you have to do some research, look into books. Okay, and in this situation, instead, the pi plus is not, okay? And the reason why it is not a Goldstone boson is because of electromagnetism, okay? U1 electromagnetism. So if you turned off electromagnetism, this would also be a Goldstone boson, but electromagnetism breaks the symmetry. And the reason is very simply, if you write the covariant derivative of the pi plus, okay, and you expand it, you have terms like the current, but more simply, a mu pi dagger plus pi minus, okay, and there would be shift symmetry of the Goldstone pi plus that goes to pi plus plus a constant is broken by this coupling, which is the electromagnetic coupling. Okay, so this is how electromagnetism breaks, and similarly also the current term. Okay, you have a current term, you have a mu pi plus the pi minus I. Okay, this also breaks the symmetry, the E times E. Okay. Now, so you have a system. The fundamental parameters in this system, what are they? Okay, at this scale, the fundamental parameters are QCD scale, and alpha electromagnetic. There's nothing else. Okay, we have set the quark masses to 0. Okay, if you turn on quark masses, that's another story. If you turn on quark masses, there's going to be a quark mass contribution to both these masses. Okay, but let's forget that it exists. It is the same. Okay, if you turn on quark masses break all symmetries and they contribute to both in exactly the same way. But let's forget quark masses. So you have only two fundamental parameters, lambda QCD and alpha electromagnetic. And lambda QCD, a good measure of lambda QCD is the mass of the hadrons, like the rho meson is the lightest non-trivial hadron, and the lightest hadron that is not a Goldstone boson. So m rho can be taken as a good measure of the fundamental scale, the scale at which these degrees of freedom emerge, pions. And now you can just apply selection rules. Okay, what do you expect for the mass of the pi plus? That's our observable. Okay, in this case we only have the leading order. We have no options. Okay, this will have to be proportional to the mass of the rho. Here is the dilatation. I'm saying pompously the dilatation selection rule, but it's just dimensional analysis. Okay, and then you haven't finished, because this is not enough, because you need to add the notion that there is a coupling, okay, E, which breaks the shift symmetry, okay, so it is like an external field that has to do with you could assign transformation properties in the bigger sense and restore the symmetry. I don't want to discuss it here, but anyway, this is the parameter that breaks the symmetry. So it must necessarily enter, okay, with a positive power into this equation. And of course, you can have E, but E goes to minus E is a symmetry, okay. If I change the sign of E, I can change the charge of the photon, so it's just a reparametrization symmetry. It certainly cannot be proportional to E, it must be proportional to E square. And then you know that it's related to a process which has no photons, okay, real photons. So the photon is absorbed, it must be emitted, must be reabsorbed, so there should be some loop. But that's just a numerical thing. So you know that there should be the usual 4 pi squares that you have when you do loops, okay? But that's not the big deal, okay? And I want to insist on that. This is just a refinement of dimensional analysis. It's just a refinement to get quickly to the thing, and that's it. We would be shocked if this would not be correct, and this in fact gives within, I don't know, factor of 2. I mean, as order of magnitude gives you precisely what you measure. Okay, that's an example of selection rule acting in quantum field theory. Okay, so, and there are other examples like this. Another example of this, meditate over, and just to draw the analogy, is the K0 bar mass difference. Okay, which if you want I can discuss that in the discussion tomorrow. Okay, so there are examples of these selection rules in QCD. Okay, and now this sets the stage for the next discussion, which is concerning natural and unnatural hierarchies. Okay, any questions at this stage? Yeah. Well, E4 is even more, right? I mean, this is the lowest possible power you can have. Yeah, sure. But one could argue that it must be square. Yes, one could. Not on the stage. Perhaps we can do it later. Yes, I think one can. Okay, so let me now discuss the next subject. So now we are approaching the the notion of, okay. So imagine a situation where you have a theory, quantum field theory, emerging from some unknown more fundamental theory, which could itself be the infrared manifestation of an even shorter distance physics, but there's some unknown physics at higher scales. And the scale here, I call it lambda UV, is a physical scale, is the analog in our mind of what the QCD scale m rho is for the pion. Okay, so it's some fundamental scale where our degrees of freedom emerge. So we will have some effective Lagrangian emerging out of this more fundamental physics, and this effective Lagrangian will be characterized by an infinite set of couplings, lambda I, relevant, marginally relevant, all of them. Okay, and these parameters, as I said before, they are functions of more fundamental parameters. They can be seen as lower energy observables over a more fundamental theory. So they will depend on the more fundamental parameters in a way that respects all selection rules. Okay, and of course there could be cancellation, but certainly we respect selection rules. Okay, the natural situation is precisely the one where nothing that looks like cancellation exists in the pattern of this parameter. In other words, that we can understand the size of different parameters in a way consistent with the symmetry. In particular, if there is a very tiny parameter, all the parameters that have the same symmetry transformation property should also be small. Okay, otherwise that would seem unnatural. So under this condition, this condition is what it's a variant of what is now recalled as Toft naturalness. Okay, that all it's a slightly more general statement because it was only talking about singular small parameters. Here I'm trying to say that one could really have a global relation of all these parameters, and you can decide case by case basis whether the whole set looks self-consistent. Okay, in other words, that, let me say it better, whether you can imagine, so the exercise is the following: whether you can imagine a set of more fundamental parameters transforming in a certain way, of which these are functions. Okay, and therefore the pattern of size of all these parameters can be understood consistently in terms of the patterns of the more fundamental parameters. Okay. Now, in this situation we call a natural situation. Okay, and a corollary of this is that when you have a very small parameter, this should be associated with some symmetry. In other words, when the parameter goes to 0, you should have some additional symmetry recovered. Okay, that's Toft naturalness. It's a criterion. Okay, it's not. There's no reason why this should be true. Okay, because there can always be cancellations. Okay. Now consider now this situation and imagine we are in the situation we discussed the first day. Imagine that there is a huge scale separation to the next location in physics, far in the infrared. Okay, assume that there is this big scale separation. Okay, now a fair question under this condition is under what condition this separation is natural. Okay, given that we have parameters, dimensionful parameters that have, certainly if you just look at dimensionality, this seems weird because you have parameters at face value that have dimension 1 under dilatation, and they're very, very different. Of course, there can be other symmetries that differentiate them, but if you just look at dimensional analysis, this, if you add only dimensional analysis, this would be unnatural because you have parameters with the same transformation properties and are very different. Okay, And it would be hard to imagine these arising from selection rules. Okay, it would be hard. Okay, if you just imagine these are functions of a more fundamental scale, this function they will be functions of this fundamental scale with some coefficients of the same order if there are no other symmetries, and then they would have to be comparable. Okay, is this clear? Okay, now and this is, I just want to go to what I was telling him yesterday, okay? Notice that the very hypothesis that there is a separation of scales, okay? The very hypothesis, it means that in the between, nothing much happens, okay? That the theory is not much, the dynamics is not much changed it's scaling trivially, almost in the between these two scales. That is to say that the theory in the between is approximately scale invariant, very much as we were discussing in the first lecture. Okay, so again, separation of mass scales, the presence of two mass scales implies, by definition, if you want, it's a tautology, that there is approximate scale invariance in the between. For it could be approximate, the theory could not be exactly fixed, could be oscillating, could be doing things, but it's not changing dramatically. Otherwise, a dramatic change in the dynamics is the occurrence of a new scale. Okay, so let's consider the situation now. Okay, and let's try to characterize it and see under what conditions we can judge it plausible, to say natural, or less plausible, unnatural. Implausible doesn't mean impossible. Okay, that's should be very, very clear. Okay, it's a dangerous field. Okay, it's not that what you say is it's just structural reasoning, and we are making a significant use of our notion of common sense, but that could be wrong. Okay, so one can address the question of whether the hierarchy is natural or unnatural from the point of view of the RG flow perspective, And let me explain this better, okay? So as I said, the theory, when there is the separation of scale, should be sitting, this is the lambda coupling parameter space. The theory should be sitting in the neighborhood of a fixed point. This fixed point could be, so it's approximately, the very fixed point is scale invariant, and we start we have to start near it. We have to be approximately scale invariant. So the starting point should be near this fixed point. Okay, lambda I in the UV. Start nearby. Perhaps I can use color chalks. The first time in my life. Blue. Ultraviolet, okay, and then you start running. Okay, then we'll see. And what the hell did I want to say? Now colors have taken away the concentration. 1 second, okay. There's something I wanted to say. Okay. So. Again, is to answer this fellow, okay? Yesterday, he told me that he was very much bored by my 45 minutes about SFT and CFTs, and I can even be agreeing with him, okay? Okay. But the point is that you see now we are addressing an issue which I think is relevant in particle physics, and the notion, a central notion to the separation of scales is the existence of an approximate being close to a fixed point, being approximately scale invariant. So there must exist a scale invariant theory somewhere nearby where we start. And I think it matters to know whether the scale invariant theory is only scale invariant or it's also conformal invariant. Okay, this is potentially relevant for particle physics. Okay, and free theories are conformal invariant. So free theories that are nearly free, like the standard model, are sitting near a conformal fixed point. But one could consider crazy situation, less normal, where the theory we sit near to is only scale invariant and not conformal invariant. And perhaps having less symmetry, having only scale and not just conformal, we have more freedom, because theories that have less symmetry, like scale invariant theory, are perhaps less constrained. Okay, they have less symmetry. Okay, so now we start flowing from this point. Okay, we are approximately conformal, and then we go towards the infrared, and we flow, and then, okay, let me now take the red. We go towards the infrared. This is not even red. Okay, this is pink. Okay, and as I already mentioned, at a certain point in this flow, some coupling, okay, some coupling lambda bar, some of them becomes 1. Okay, becomes of order 1 in this order 1. This is to say, order 1 meaning that this coupling causes an order 1 deviation from the fixed point, or in more technical terms, this coupling affects the energy, the matrix elements of T mu mu in such a way that they are now large on the T mu mu is an operator of dimension 4. Okay, if T mu mu is 0, you have conformal symmetry. It's easier to talk about conformal symmetry because you can just say the theory is conformal when T mu mu is 0. Okay, here T mu mu is 0. Here it gets bigger, slightly bigger, and when some of these couplings become large, how large? Just you can phrase it in terms of how large are the matrix elements of T mu mu. Then you are order 1 away, because T mu mu is the divergence of the dilatation current. When the divergent is not suppressed, then you don't even have an approximate scale invariance. Okay, and this is precisely the point where you reach the new regime, the new scale. Okay, an example of that is in QCD. Use white things. In QCD, there the relevant coupling, the lambda bar, is alpha strong. Okay, that runs with energy. Okay, it runs, it grows when you go towards the infrared, and at a certain point becomes of order 1 at E of order 1 GV. And this is where you enter into a new regime. Okay. More simply, in scalar field theory, let me say it in the same way. The relevant parameter is lambda bar 2, is the dimensionless, is just the running mass divided by E square. It tells you how important the mass deformation is, and when this becomes of order 1, you are at the scale of the mass itself, right? Okay, so now these are simple cases, but we can take a broader perspective and just look at the general flow. Okay, what we can say is that, okay, we have how can I erase? Let me just take some space here. Let me take this space here. So in general, we have this RG equation, DDE. By the way, in what I'm writing now, E is mu. Okay, I take E as the normalization scale. Okay, sometimes I will write E, sometimes I write U, depending on how I feel. Okay, but it's the same thing. Okay, remember, for pedagogical reasons, I introduced the RG flow in terms of really physical, changing the energy of the process, but you could also view it in changing the mu the mu scale in the dim reg. It's the same thing, okay? But for pedagogical reason, I called it E, and so I keep calling it E, but if I were more formal, I would call it mu, okay? The same thing. So now this lambda I is going to be some beta function. The lambda I bar, okay, all of them, truly the dimensionless couplings, normalized suitably in such a way that they are dimensionless, just some powers of the lambda I, okay, like this. And the infrared is so let me also, this can be written also in terms of a logarithm, dt, where do you use the same notation? No, minus ddt, where t is log of the UV scale divided by E. Okay, that's the way you can write it. And as I said, the infrared is in this RG flow, dd of lambda I bar. In this RG flow, the infrared is the scale where some of this coupling, after flowing in this coupling space, become of order 1. So you start and you flow. Now the separation in scale between this point, see, going from here to there, this is just like a time derivative. This is RG time. This is what you normally call RG time. I'm just giving picture, okay? I'm not telling you, proving anything here. I'm just giving you some picture, okay? So this is, you can view this flow really like a motion, okay? This motion to go from here to there takes some time, okay? And this is the velocity, okay? The velocity is just the beta function, okay? It's clear that to go from here to there, it'll take big or small time, depending on how big the velocity is. That is the beta function, right? So if you want to have a big separation of scales, okay, that is lambda UV is large, the time to get to the infrared, the RG time to get the infrared is the logarithm of lambda UV over lambda IR. So if you want this separation of scale to be large, the time that it takes to go from the UV to the IR will have to be logarithmically large, okay? Will be, so if this is 20 orders of magnitude, you will have t to be about 20, 30, okay, something like that, okay? So it should be large in that sense, okay? So, as I said, you know, if you want this separation to be large, you have to it needs to take a long time to flow away from the vicinity of this point to there. Now, with this picture in mind, we can so the question of the naturalness of the hierarchy is just a question of the naturalness of the slowness of the motion, okay? So the separation of scale is naturally large, okay? The hierarchy is naturally obtained if the beta function is naturally small, okay? If the evolution is slow, it can be made, can be viewed as naturally small, okay? Again, according to our criterion of selection rules. And this you can decide more easily on a case-by-case basis, okay? And now, the smallness of the beta functions, okay, in the language of RG flows, okay, is a way of measuring the stability of the fixed point, okay? Stability of the fixed point tells you how rapidly you flow away when you go towards the infrared at a given point, okay? It's clear that this point, the stability of a point tells you how big is the area where you move away slowly, okay? So the smallness of the beta function has to do with the notion of stability of the fixed point. Now, there are two standard, now we come to more concrete statements, okay, perhaps. There are two standard ways of achieving this slowness, okay, and you'll see in a moment. And these two standard ways are associated in one way or another to compositeness and supersymmetry as far as the problem we will discuss tomorrow, that is the hierarchy problem. Okay, these are the two standard ways. There's a third way that came recently to the fore, and the author of this third way is here sitting in the 5th row, okay, to my left, okay. And that's a different thing. I'll show probably some transparency at a certain point about this. This is a bit crazier. It's interesting, but it's a bit crazier, okay. Do you agree, Alessandro? Let's see the transparency. Let's see the transparency. So you don't agree. Here I call it the third unorthodox option. Logical possibility, but I think it cannot be realized in practice. This is what I wrote. Okay, I had forgotten this. This is a more logical way of saying it. Okay, now, before going to illustrating the two standard cases, okay, let me before discuss what situation is certainly not doesn't certainly look natural, okay? And that is the situation where you have, just to give you an idea, what is the situation that what does not look natural? Okay, this is a situation where you have the fixed point here. As I said, you see now the notion of naturalness is related to what features do the beta function around this fixed point have. It has to do with the properties of the deformation of the fixed points. Okay, how you flow away from it, how fast, how slowly. Okay, again. This brings again the importance, okay, of fixed points and their deformation, which is scalar invariant field theory and conformal invariant field theory. Okay, of course the symmetry is at the fixed point, but what the real meat is not when you have the symmetry, but when it's broken, okay, and broken by small effect. That is to say, in the neighborhood of the fixed point. So the situation which certainly doesn't look natural is a situation where the fixed point admits very relevant deformations, okay? Operators of dimension, scalar operators that you can add to the Lagrangian of dimension less than 4, like a scalar mass term. And in a situation where there's no selection rule other than dimensional analysis or symmetries broken by big effects to tell you that this coefficient should be small, okay? So the example is scalar mass. So an operator O, okay, so the case this is when you have very relevant deformations or the fixed point, okay. This is a very pompous word, and in the theories we can really compute and work with Mathematica, as Alessandro likes to do. We call it a scalar mass, okay? But in a in a grandiose way, you can say very relevant deformation, okay? Now, so an operator whose dimension delta I is less than 4 significantly, so delta I equal, I don't know, 2.5, 2, 3, okay? Of course, in free field theories, the dimensional operators are always approximately integers, so in free field theory, in near free fixed point, we only have either dimension 2 or dimension 3. There's nothing, which is either scalar mass, cubic scalar, and fermion mass, 2 and 3, okay? Now, cubic terms and fermion masses are easily protected by symmetries, as I will say in a moment, okay, principle. So they're less problematic. Scalar masses are tougher, okay, and if the scalar is interacting, okay. So the example is a scalar mass, okay, m square phi square over 2, and here the expectation, sorry, I have to go on this time on this side, okay. The expectation is that m scalar, just by selection rules, is given by the only dimensionful scale we have, which is the UV scale. We're just applying dimensional selection rules, okay. Time, in principle, there may be additional suppression because of other global symmetries that under which this mass transform and this does not transform, okay? Very much like in the case of the pion. In the case of the pion mass, you saw there was the raw mass playing the role of lambda, and then there was a gauge coupling, so a coupling which is small but not too small, okay? And now in the case, and that case serves as a template for what I'm saying here. In the case where you have a scalar, very much like the pion, which is interacting, like it has gauge interaction, you have interactions. Here you cannot expect anything better than what you get in the case of the pion, okay? So and this is what we find in all the models we can build, whether the supersymmetry, what is the underlying reason that determines the emergence of this theory. We typically have here like a coefficient like this, okay? Coefficient which, unless the coupling is 10 to the minus 20, does not give you a big hierarchy, okay? Okay, if anything which is reasonably coupled, like we see all the other couplings, perhaps this can be 10 to the minus 2, 10 to the minus 3, but it cannot be 20, 30 orders of magnitude. Okay, so normally what you have in the situation, you have, let me not even write that, you have some coefficient which, okay, you can leave it free, and this is your selection rules, and then unless you have a specific symmetry, okay, which I will say in a moment. So if you don't have any very, very specific symmetry, you expect this to be not much less than order 1. And in this situation, it's clear that lambda IR, so you want this to be your lambda IR, and in order, so then it's clear that to get a hierarchy which is of a certain size, the coefficient, the dimensional coefficient, should really carry all the weight of these hierarchies. If the hierarchy is 20 orders of magnitude, the coefficient will be suppressed by 40 orders of magnitude. So all the essence, all the hierarchy is coming from having a small coefficient. Now the question is understanding why. So if you the only way to understand the coefficient of that size would be to have some selection rule that tells you that coefficient is from under symmetry. If there isn't any very strong selection rule, any strong symmetry protecting it, then this is what you would have. And let me say this from the so then this seems it seems like in this situation you have to hope for a cancellation, like the one you have when you choose the random atom that has exactly the property that the mixing of two levels of different spin when in an electric field is much less than would you expect from selection rules. Perhaps in trying a zillion of models, at a certain point you will find one where C is 10 to the minus 20. If you want to get 10 to the minus 20 hierarchy, you try 10 to the 20 models, then probably that's the idea. I don't know whether I should anticipate something, but once a colleague, so there is a problem, as I'm anticipating something, there's a problem, as you know, in supersymmetry, there seems to be some tuning of parameters, and this tuning can be 1 in 100, 1 in 1,000, depending on the taste. And we are, in the community, working on this problem about in the same order of 1,000, okay? And then the colleague who was all excited that had found a model where there was a cancellation randomly explaining this thing, and I said, of course, we are 1,000 people, things are randomly distributed, there's going to be one who has a cancellation of 1 in 1,000. That's you, okay? But that's doesn't mean much. Okay, so now this is the let me say from the point of view of the RG flow, because it's good to compare it to what I'm going to say in a moment. So here the RG flow, in the case of the mass, okay, the dimensionless parameter which controls how far or close we are to the fixed point, which is m square e square, runs EDE of lambda bar 2 is, where you just do the right things, it's minus 2 plus gamma. Gamma is coming from the running of m, is the normal dimension of the mass, okay, times lambda 2 bar, which is basically, in weakly coupled theory, this is minus 2, roughly minus 2 lambda bar, okay? I'm saying something obvious, okay, but let's, it's good to see it in perspective. Now, you can solve this equation. This is ddt. Let me say this is the RG time. This, oh, yeah. This is minus ddt of lambda 2 bar. Okay, so ddt, I'm writing triviality, I'm aware of doing it, but I'm doing it. 2 bar, just to compare to what you have before, and then plus, sorry. And then the solution is I have to erase this. Solution, no, I do it here, is lambda 2, no, I have to do it here, is lambda 2 bar is equal to e to the 2t lambda 2 of 0, okay? And if you want, so the RG scale, the IR scale is the scale where this is of order 1. So this is e to the 2t IR, lambda 2 of 0. This is the condition. So if you invert this, then you have that lambda 2 of 0. The initial value of your deformation parameter should be e to the minus 2 TIR. Okay, so in order to have a large hierarchy, you should be exponentially close in terms of the RG time to the fixed point. Okay, to be very, very close to the fixed point. So in the case of a very relevant parameter amounts to the fact that to get a larger hierarchy, you have to. The reason why you run slowly is because you started very, very close. This point is fixed, and it takes a lot to move away. It's like when you start rolling from the top of a hill. Okay, so you have to start very, very close. Okay. So that's the situation which we consider not natural. Let me come now to the relevant situation. Okay, so there are two relevant situations. There are two natural situations. Sorry. Let me speed up. So there are two cases. Okay, the first case is the one where the fixed point does not possess any very relevant deformation. Or strongly, let me say strongly. That is, again, a complicated way to say that the theory of the fixed point, only the lowest dimensional scalar that you can add to the Lagrangian and make it flow at the fixed point has dimension near 4. Okay, 4 minus epsilon, or exactly 4 as a function of another parameter. So it's near 4. It can be either near marginal or marginally relevant, something like that. So example of this, and of course, if you have no relevant operators, then the flow will be slow. Okay. In particular, if you have no relevant operators, imagine the limiting case where you have no relevant operators. What happens? You go on the fixed point. You'll never reach the infrared. The infrared scale is infinity. You'll never get there. Okay. Other than going towards the infrared, you will go back to the fixed point. Okay. So then there is the situation where you have very relevant operator, boom, you will go away unless you start very close. And then there is a situation that we are interested in. Perhaps you can say that this is tuned, but which is in the between, where there is a broad region in the neighborhood of the fixed point where you flow away slowly and then you reach. So I'll give you an example. The example of this is given by the Young-Mills theory. Okay, Young-Mills theory, if I have all computations correctly, in terms of the parameter G Young-Mills and color, let's say SUN Young-Mills. So let's call this parameter lambda, okay, or lambda bar lambda, okay. In terms of this parameter, this is the coupling, okay. In terms of the coupling, you know very well that the beta function, okay, ddt of lambda is minus 2 lambda square, okay. The coupling comes from loop effects. So remember before, for the scalar mass, ddt of no, it's 2. ddt is negative, so t is negative. So this was twice lambda. Okay, this was the equation in the case of the mass. And here we have very similar equation with a tiny little detail different. Okay, again, there are no small parameters. It seems like it seems the same, but the crucial thing is that there's a square here. Okay. Okay, I've just taken, this is a measure, this parameter is a measure of how strongly coupled the theory is. When this parameter becomes of order 1, you're strong. So is the coupling, this is the parameter that counts loops roughly, okay? And let me roughly tell you what are the things. This is just the typical loop counting parameter, but there is an NC, given that you have NC colors, and then there is a 11/3, which is a rough measure of the fact that you have object with spin. Okay, but this is just a numerical thing. Okay, so when this coupling is of order 1, becomes of order 1, perturbation theory breaks down. All our perturbative series no longer make sense. Okay, this is where we have, this is what we interpret. Okay, our interpretation, like in QCD, this is Young-Mills. There's no quarks. This is pure vectors. Okay, the reason why I don't put quarks is because in this theory, in the case, sorry, I should say, in the case of Young-Mills, you cannot write any operator of dimension less than 4 to start with in your Lagrangian. You cannot write anything. Okay, I forgot to say that. In Young-Mills, you cannot. There's no fermion mass, there's no scalar mass, there's only the gauge kinetic term. Okay, there's no operator at classical level. There's only an operator of dimension 4. Okay. And then when you turn on quantum mechanics, this operator of dimension 4 starts evolving. Okay, the associated coupling evolves, and it evolves marginally so. Okay, and it grows towards infrared slowly, because it's a marginal, slowly in the sense that it doesn't run linearly like this. Okay, it does not have a classical dimension. You see here, in the case of the mass, there is already running at the classical level. And this is just the dimension of the classical dimension of the coupling, while here the classical dimension would more be like 2 lambda. Okay, so if I factor it out, the coupling has a dimension which is proportional to the coupling itself. So that tells you that as soon as the coupling becomes a little bit weak, okay, if the starting point is not strongly coupled but slightly weak, where lambda, I don't know, it's 1 in 10, okay, then the evolution is very slow. Okay, and you can see that by solving the RG equation. Okay, you solve the equation, and let me just give you the end result. It's the other way around. Now I use the T. So 1 over lambda bar, lambda is 1 over lambda of 0. This is the solution, okay? Minus T, minus 2T, okay? This is the way it evolves. And the scale where, so roughly you have that, the scale where if you start in a regime where this is small, okay, where this is say 1 in 20, something like, imagine something small but not crazily small, okay, you can say algebraically small, in 10th, 20, okay, and the scale where this becomes of order 1 is the scale where basically this 2T cancels most of it, okay. So the strong scale, the IR scale, the scale where it cancels exactly corresponds to lambda infinity, is what you normally say is the Landau pole of Young-Mills, okay, in the infrared, okay? But you don't need to get to that. It's enough to say it's of order 1, and the IR scale corresponds to 2T equal 1 over lambda 0, okay? And sorry, before I need lambda 0. Here, to get the hierarchy is lambda 0 equal e to the minus 2t IR to get the hierarchy, and here lambda 0 from this equation, lambda 0 is 1 over 2t IR. So lambda 0 should be small, okay, but should not be exponentially small. Should be power-like small in the RG time. So which is a big difference, okay, numerically, okay. It doesn't take that much effort to get this, and written in terms of the scales, okay. This this can also be written more correctly in terms of lambda IR over lambda. This is probably even more clear. Okay, this is e to the minus 2, e to the minus 1 over 2 lambda 0. Okay, so that means that in order to get a hierarchy of an exponential hierarchies between the two scales, it's enough to have a moderate algebraic hierarchy in lambda 0. Say lambda 0, 1 in 20 already gives you 30, already gives you 30 orders of magnitude, 10 or so orders of magnitude of separation between the two scales. And so this is the reason, if you want, why in QCD, which is somewhat related to this, we don't worry about the value of the QCD scale, because it's so much affected by the value of lambda 0. Okay, if it's enough it depends exponentially on lambda 0. So it's enough that lambda 0 is in a region where it's weak, that this hierarchy is large. Okay, exponentially large. Now another example that more abstract, okay, of in this class of theories is given by models. Okay, so you can also think that the fixed point is some abstract. Let me give you another example of this. Imagine the fixed point. Okay, the lowest dimensional scalar operator of this theory has a dimension. It's O. Okay, it has dimension 4 minus epsilon. Okay, where epsilon is an algebraically small number. Okay, a 10th, 20th. Okay, not 30 orders of magnitude. It's just slightly small. That could happen by some cancellation. The reason from the fundamental theory that perhaps this parameter is controlled by some fundamental parameter, but you don't expect to get much effort to get something like this in principle. Okay. But there may be no theory with these features. Okay, that's a different. Now, theories of these features have been partially constructed using ADS-CFT. Okay, or same class of reasoning. Anyway, so let me just simply tell you how things work here. Imagine you have an operator like that. Okay, and now you expect a deformation that goes like some coefficient. O 4 minus epsilon. And what do I get here? What do you expect to get here? From dimensional analysis selection rules. Lambda to the epsilon, right? Here you have lambda UV to the epsilon. Okay? And I don't want to go again through the story. This guy runs very slowly. Okay, the corresponding coupling lambda bar is C lambda to the epsilon divided by e to the epsilon, and dd bar ddt of lambda bar is epsilon lambda bar. It's somewhere in the between. Okay, this guy here, it's linear like in the case of the mass. But the coefficient is not 2, is epsilon. Here it was nonlinear. Okay, the coefficient was the coupling itself. Okay, so you could make it dynamically small. So the coupling is small, the dimension becomes small itself. Here, for some reason, we end up in a situation where there is a small dimension, and then again, the evolution will be slow. Okay, there's a slow evolution, and we expect the hierarchy to be naturally large. How do we see it? Well, just more directly, if this is the parameter that appears in the Lagrangian, we can directly read what the corresponding mass scale is. It is the whole thing. This is the infrared scale. Okay? You just look at the Lagrangian. It's the parameter that appears in the Lagrangian, the infrared mass scale, and then you can relate it. Lambda infrared, the epsilon, it is equal to C lambda UV to the epsilon. And then if you consider the hierarchy, lambda IR, the ratio of lambda UV, this goes like C to the 1 over epsilon. And again, it's a relative of this exponential suppression. Here is slightly different. Again, you don't get anything from nothing. Okay, it's clear that to get a hierarchy, you need somewhere something small. Here we needed lambda 0 to be not 1, but slightly less. Here we need this parameter C to be less than 1. But let me give you an idea, okay? If epsilon were to be 1 in 10, okay, which is small but not too small, and C, there's also another accident there, and C is 1 in 10, then the hierarchy is 10 to the minus 10. Okay, so it's 10 orders of magnitude. So this again gives you an idea of a situation where without asking much from parameters that do not transform under any symmetry, as far as we can tell, here I'm assuming that the only thing I'm assuming here is dimensional analysis. There is this mass and there is a dimensional parameter which does not transform under any symmetry. There's nothing protecting it. I'm not asking it to be 10 to the minus 30. I'm just saying that you can get a hierarchy if this is. So this is a way to generate big separations. Any questions? And then there is the option, the second option. The second option, I'm afraid I will not have time to talk about Strumia, but if you want, if I have, I'll do it probably. If you're not starving, okay? So now this is the first option, and I should say that this option here is the option that was okay. Okay, I will not say it. So this is option. Okay, this is just slow. All operators run slowly. Okay. Then there is a second option, which is quickly said. Okay. The second option is that the fixed point does possess relevant operators, but their coefficients can all be assigned non-trivial transformation property under some symmetry. Or let me say better, their couplings, their coefficient transform under symmetries. Let me say it simply. Okay, so in this situation, you do have relevant operators. Okay, so for instance, so you have operators O, I with delta O with delta less than 4. Okay, so you have the corresponding coefficient is going to be C lambda to the 4 minus delta, and this, if delta is 2, this is okay. However, this C transforms under symmetry, under a symmetry which is very well respected by all the other couplings, okay? And in this situation, you can say, well, okay, if for some reason the fundamental theory, which I may not know, but if for some reason the fundamental theory has its approximate symmetry, then I can understand why this coefficient is small. I'm not trying yet to think where the symmetry would come from, whether it's coming from worldsheet instantons or whether it's coming from RG-flow in the other stage of running, whether it's just a gift of God, I have no idea. Okay, but there is this symmetry. Okay, you may be dissatisfied with any of these three explanations. Okay, but there is at least a rationale for that, and then we can. And examples of these are QCD. Okay, an example of this is QCD, where you have the Lagrangian is, of course, the gauge kinetic term, which is marginally relevant, as I discussed before. I erased, of course. Then there is the gauge kinetic term, the fermion kinetic term, and then there is the mass term, psi bar I Mij psi j left, right, plus emission conjugate. Okay, you have a mass term, and of course, if the mass so the mass term associated with operator dimension 3, if the mass term is scales like the UV cutoff, then you have no hierarchy. Okay. However, the mass term in this theory respects at the level, at least, of the renormalizable part of this Lagrangian. Then God knows what happens at higher levels. That depends on the fundamental theory, exactly. But at least at this stage, it can be endowed. It can be endowed with a chiral symmetry under which these masses transform. Okay, it's a chiral group, and you can associate the smallness of this coefficient. That is to say, let's say in the space of couplings, there's the fixed point here, and in the space of couplings, there's a surface that goes through the fixed point, and this surface is the surface M equals 0, and it's a surface of enhanced symmetry. And the assumption, okay, in this case, is that, okay, if you're not on this surface, if you're away from the surface, then if you're even slightly away from the surface, you flow away rapidly, because away from the surface there are relevant operators turned on. Okay, on this surface, the surface M equals 0 is the one where this coefficient is 0. Okay, I imagine there are also the other couplings irrelevant. Certainly there's the gauge coupling. Okay, and so the picture is that for some reason, okay, your initial conditions are near this surface, and we consider initial conditions that are that seem peculiar, like these ones here, where the mass is 0, to be acceptable if the surface we are approaching to get what we want, this is a hierarchy, is a surface of enhanced symmetry. Okay, in the limit where this mass would be 0, we would have an additional symmetry, and we may like it or not, but it has a certain specific feature. It's not yet, so this request, so this is just a statement, okay, if you want. Now, how can we, why should we like this, okay? The fact that the small parameter is explained by the symmetry. Well, we could understand, certainly in terms of selection rules of the fundamental theory has the symmetry, but that is not satisfactory. You can't be keeping a symmetry. Where the hell is the symmetry coming from? Well, symmetries can easily be constructed. Whenever you have a parameter, and that's just, it's hard to quantify this, you need the practice of model building. But whenever you have a parameter which is small because of a symmetry, there is a way, and it'd be interesting to see examples where this is not true. If you can bring them to me, I'd be curious. When there's a parameter that transforms under a symmetry, there's a way of extending the theory, or viewing it differently. Let me go to the next level, where this smallness of this parameter has an explanation, even without the symmetry. Okay, where the symmetry is emergent. Okay, so in particular, in this case here, this symmetry here, okay, could be originating from a previous running. Okay, imagine this is the example I was saying before. Imagine, but let me say it better, and then I'm done. Okay, what I'm saying is that I want to use the right word. The explanation of a smallness of the smallness of a parameter using a symmetry sets the stage for the explanation of the smallness of the parameter without really relying much on symmetries. That's what happens. Okay. Let me give you an example, just a very simple example. Take neutrino masses in the standard model in the Cabibbo-Fermi theory. Since we are in Italy, I'm doing Cabibbo-Fermi theory. Okay, the theory of the standard model with just the quartic interactions of Fermi, add leptons, and then introduce also flavor mixing. In this theory, and you have neutrinos. In this theory, you have no reason to think neutrinos should be light in terms of symmetry. Okay, you could make them, you could give them a mass. Okay, but you say, I'll notice if I give a mass to neutrino, Majorana neutrino here, I'm just adding left-handed neutrino. But if I give a mass, I break lepton number. there is a symmetry. Then I say, oh, okay, perhaps there is a symmetry. Well, where the hell this symmetry is coming? I have no idea. Then you go to the next layer. You go to the standard model with the doublet Higgs. You write the theory, and you discover that the neutrino masses come from dimension 5 operators. They're irrelevant. Okay? And in that theory, provided for some reason, which we may not have, you have a separation of scales, this explains why the neutrinos are light, because they're coming from higher multiple effects. They're coming from irrelevant operators. Maybe the wrong explanation, but it gives you an example of how a symmetry of the low energy theory can be understood as an accidental symmetry in the full picture. Okay? And another example of that, which is very similar, is the one I gave yesterday. Okay? Imagine you have some fermions, okay, QQ bar, and their mass, because of quantum numbers that I'm not writing here, that tie them together. There are quantum numbers that tie them together. Okay, so you can only write this operator. Okay, you cannot write QQ bar. Okay, there are some quantum numbers of QQ bar of Q and I, J, K, L that they have to be contracted. So there's no way to write a QQ bar operator which is invariant under, let's say, some gauge gauge symmetries, for instance. Okay, and then, so this thing is coming from, this is what happens in Technicolor, by the way. And so this is coming from 1 over m whatever, m Planck perhaps squared, okay? And so the theory, so m Planck square is the, so you have this situation, sorry, okay, let me write it here, and then I'm done, okay? You have m Planck, you have lambda uv, and then you have the effective theory, which is the theory below some lambda uv. Lambda uv is the scale where these guys condense. Okay, this TT bar confined like in QCD. There is symmetry breaking of the corresponding gauge symmetry. That it goes in the Higgs phase. So the net result of that is that this 4 Fermi operator spits out when these acquire expectation value something like lambda uv cube. Lambda uv, from the point of view of the whole theory, is an infrared effect, okay? It's a lambda IR of this bigger theory. For us, it's the UV. For the other, is the IR, okay? And the m Planck square. And if there was a separation of scales, the mass of the fermions has this suppression, okay? And it is small. It's just an accident, okay? Because it's an accident due to the fact that the theory in the higher layer, of the onion, had an accidental symmetry, okay? So another example of an explanation of a hierarchy by symmetry is given by supersymmetry. Okay, in that case, I don't even write it. You have fundamental scalars. Fundamental scalars can have masses. You can write fermion masses. So these are relevant operators of dimension 2. However, the scalar masses under the scalar masses of a supersymmetric theory almost always generically break supersymmetry. Okay, so again, in that case, supersymmetry is essentially a generalization of chiral symmetry scalars. You can have exactly like for the case of QCD, an explanation of the smallness of the hierarchy. And again, even in this case, people normally say, "Oh, supersymmetry explains is natural, but doesn't explain why there must." No, it's not true. Okay, supersymmetry, again, very much like in the chiral case, the fact that there is a symmetry that explains the smallness of the soft term supersymmetry sets, again, non-trivially the stage for a dynamical explanation of why the soft terms are small. And the reason is very similar, is somewhat related to that, but it's a long story. But the neat statement is the following. Supersymmetry can only be broken by non-perturbative effects under broad conditions. Can either be broken by 3-level effects or by non-perturbative effects. Cannot be broken by loop effects. So the breaking of supersymmetry is either of order 1 or of order e to the minus 1 over g squared, where g is some coupling. Now, under, again, broad condition, you can be in a situation where this does not happen, and you have just this. Okay? And again, if the coupling is weak, but say 1 in 20, again, you get the same exponential hierarchy that I was talking about before. So again, this is another example where the presence of a symmetry sets the stage for a deeper explanation. Okay, thank you.
questions? Sure. Wait for the microphone. Wait for the microphone.
The 4 minus epsilon. That's the dual version of the Goldberger-Weiss mechanism. Randall-Sondrum does not explain anything. It's Randall-Sondrum with the stabilization of the radius that gives you a dynamical explanation for the hierarchy. They were just having, I mean, they set the stage in a sense, and then the explanation came. At that stage, there was no real explanation. But it was a good idea, and it set the stage for an explanation that came after a few weeks. But if you look at Goldberger-Weiss, and you translate it from the ADS to the CFT language, it's precisely that. That's, for instance, explained in a paper I wrote long ago with Zaffaroni.
Any other question? Okay, if not, we thank Professor Rattazzi again.